Asking how big the universe is seems like a silly question. I mean, like, it's big, really big. How big, you might ask? Oh, I don't know. There's probably a your mama joke in there somewhere. But suffice it to say that it's ginormous. But ginormous isn't really a scientific term, although it should be. So seriously now, how big is the universe? Well, the first thing you need to realize is that many people misunderstand exactly what that question is asking. We first need to distinguish between the entire universe and the universe visible from Earth. Those are different things. So how much of the universe can we see from our vantage point here on Earth? Well, light has a finite speed, specifically about 300,000 kilometers per second, or about 186,000 miles per second, which means that when you see an astronomical object, you're seeing it like it was in the past. For instance, it takes light from the sun 8 minutes to get to the Earth. You probably knew that. But that has bigger implications. For instance, that means that there is a sphere around the Earth with a radius of the Earth-Sun distance where light takes 8 minutes to travel to us. And that sphere idea is true in general. There is a sphere around the Earth with a radius of a light year. If we could somehow send lots of super bright lights a light year away to surround the Earth and briefly blink them, what would happen is that the light pulse would take a year to get to the Earth, and they'd arrive at the same time. When we saw them, we'd be seeing a blink that was a year old from objects located a light year away. We can take this idea to the extreme and ask, what is the oldest thing in the universe? And that is, by definition, the moment the universe began. That happened 13.8 billion years ago. If the universe wasn't expanding, the farthest thing we would see would be a sphere centered on the Earth with a radius of 13.8 billion light years. This is what we call the visible universe. Inside that sphere, light has had time to get to us. Outside the sphere, it hasn't. We can't see anything outside that sphere. Now I should caution you and point out that the numbers quoted for the visible universe are true only if the universe isn't expanding. Of course, it is expanding, so the situation is a little more complicated. I made a video about how that changes things, and you might even want to take a look at it. But the bottom line is that there's a sphere centered on the Earth that is the extent of the visible universe. Is that how big the entire universe is? The answer to that question is almost certainly no. The universe is bigger than we can currently see right now. And you kind of already knew that. For instance, as we look out and see the light from the beginning of the universe today, we can see out to some distance. If we look again tomorrow, we will be able to see out to that distance plus an additional light day. That's because light traveling over the course of those 24 hours will be just getting here tomorrow. And inexorably, day after day, we'll be able to see a larger and larger sphere of the universe. There are locations that we cannot see today because the light simply hasn't had time to get to us that we'll be able to see tomorrow. Again, this ignores the complications due to the expansions of the universe. We'll get to that in a minute. So if the entire universe is larger than the portion we can see, how big is it? Well, to answer that question, we need to back up and be a bit more careful. Let's start with talking about the oldest and most distant thing we can see. As it happens, we can't see the moment the universe began. That's because the early universe was so hot that light couldn't pass through it. You can sort of think of it like a fog. However, there was a moment about 380,000 years after the Big Bang when the universe cooled enough to become clear. The temperature at which that happened is about 3,000 degrees centigrade, or about 5,400 degrees Fahrenheit. Everywhere in the universe, the temperature was identical, and at 3,000 degrees, it was glowing hot. So you'd think that when we looked out with our telescopes, we'd see a glow about like what looks like when you see inside a steel mill. But this is where the expansion of space comes in. Since that moment, the universe has been expanding and cooling and even stretching space. The upshot of that is that what once would have been viewed by the human eye as white is now no longer visible and can be only seen by radio antennae capable of detecting microwaves. For that reason, this oldest thing that we can actually see is called the cosmic microwave background, or CMB, and the temperature of the universe in the current day is now 2.7 Kelvin, or minus 270 degrees centigrade, or minus 450 degrees Fahrenheit. Pick your favorite units. So that's the first big thing. This microwave radiation that measures that the current temperature of the universe as 2.7 Kelvin is a fossil remnant of light emitted when the universe was about 3,000 degrees. This temperature is almost the same everywhere, but we've learned that there are very small variations in the universe's temperature. These variations really are incredibly tiny. The hottest and coldest spots are only 0.01% different from the average. Our current best measurements of these variations comes from a telescope in space called Planck. Astronomers using the Planck Observatory have measured the entire sky, and their map of these temperature variations is what we see here. The blue spots are colder than average, and the red spots are hotter. So those temperature differences are pretty and all, but what do they have to do with the size of the universe? It turns out that these variations were caused by sound waves in the hot universe just before it became transparent. And because we know the temperature of the universe was at the time, and we've measured the total amount of matter we can see in the universe, we can calculate the wavelength of those sound waves. It's a complicated calculation, but it's a straightforward one. And I want to emphasize that there's no guesswork on this. We have heated matter to these temperatures, and we've measured the matter we see in the visible universe. We know a great deal about the wavelength of sounds that were present. Sound in the early universe is pretty much the same as sound you used to hear me. Sound is transmitted through variations in the density of air, and you can hear a variety of frequencies. In the early universe, the regions of higher and lower density, due to the sound waves, result in hotter and colder spots in the cosmic microwave background. And given that we know the wavelength of the loudest sound in the universe before it became transparent, we can calculate the angular size of the most common sizes of hot and cold spots in the microwave background. Further, we can calculate what size is most likely, and it should be 1 degree as viewed from Earth. Okay, so now we're getting somewhere. We have a firm prediction of the size of hot and cold spots. This brings us closer to our question, which I remind you is the size of the universe. Now that prediction of 1 degree depends on the shape of the universe. Remember that Einstein's theory of relativity says that space and time can bend and morph. Space could be one of a variety of different shapes. It's hard to imagine this in the 3 dimensions that we know space really is, so we have to substitute a 2-dimensional analogy. Bear with me. A flat 2-dimensional space is like the surface of a table. Flat means flat. But a 2-dimensional space could be like the surface of a globe, where, if you kept on walking, you could, in principle, end up back where you started. This is called a closed space. Another possibility is space could be shaped like a saddle. This is an example of what is called an open space. So those are the 3 basic possibilities of the shape of space. How does that fit into our question? It comes down to the fact that light travels in a straight line in space. But if space is curved, then we can get fooled. Let's use the hot and cold spots in the microwave background to see what I mean. If space is flat and a distant spot in the microwave background is 1 degree wide, then we will measure the size as 1 degree. This is the simple mathematics of triangles that you learned in geometry class, where straight lines travel in, well, straight lines. But that behavior doesn't have to apply. Let's see why. For instance, if two ants were in flat space and they were separated by a certain distance and started walking parallel to one another in a straight line in that flat space, they will always stay the same distance apart. If you do the same thing on a closed or spherical space, the two ants will eventually run into one another because straight lines in curved space are curved. This is like lines of longitude on a globe, where they are parallel at the equator, but intersect at the pole. And the opposite is true in an open space, like the saddle space. There, the two ants, initially a fixed distance apart from one another and walking in straight lines, will eventually diverge and get farther apart. That's just curved space for you. So this has consequences when measuring the apparent size of these distant spots in the microwave background. If space is flat, the line that crosses the spot you're looking at and the two lines that go from the edges of the spot to your telescope form a common triangle. But in an open or closed curved space, the triangles are distorted. Let me be more specific, because this is super important. In a closed or spherical space, what one would expect to be a straight line is curved in a specific way. The crucial effect is that the angle of the triangle near your eye is bigger than if space wasn't curved. The opposite is true for an open or hyperbolic space. Here, the curvature is in the opposite direction. We see that the angle of the triangle near your eye is smaller than if space isn't curved. Now, the telescope can't see the whole path traveled by the light. All it sees is the angle of the light coming into your eye or the telescope, with a closed or spherical space being bigger than expected, and the angle seen in the open or saddle-shaped space being smaller. And if we apply this to the spots in the microwave background, this means that a spot that is 1 degree wide in flat space will be different in a curved space. So this is a perfect way to test whether space is flat or curved. In a flat space, the dominant size of the spots should be 1 degree. If space is curved and closed, the spots should look bigger. If space is curved and open, the spots should look smaller. So what did Planck and other experiments find? A drum roll, please, maestro. The measurements found that the size of the spots is 1 degree. From that, we conclude that space is flat. Or can we? Well, yeah, sort of. But that's an incautious statement. Physics is an experimental science. When we say that the Earth is flat, what we mean is that the measurement is consistent with being flat. But that also means that the measurement is consistent with a tiny bit of curvature. For example, if we're at the beach on the ocean and look at the horizon, it surely looks flat. But in spite of the claims of some people, the Earth is most certainly not flat. It's a sphere. So you have to keep this in mind. What appears to be flat can indeed be curved. And when we measure the Earth, we can only say that it appears to be flat. And that's true of space as well. Space appears to be flat. If, and I repeat, if space is flat, then the universe is infinite in extent. Our visible universe is just a small bubble in an infinite sea. Similarly, if space is shaped like a saddle, what scientists call a hyperbolic or open space, space is also infinite. But what if space is closed and shaped like a sphere, but so big that it looks flat, like the Earth can look flat? Well, in that case, space is not infinite, it has a finite size. So now we're getting somewhere. If the universe is closed, how big is it? Well, if you do a careful analysis using the maximum possible curvature allowed by the best measurements, you find that the universe can be no smaller than 250 times bigger than the visible universe. So that's your answer. I mean, we've always kind of thought that the universe is big, but now we can hang a number on that. The visible universe, meaning the part of the universe that we can see using our instruments, is a sphere centered on the Earth and, taking into account the effects of expansion, with a diameter of 92 billion light years. However, the entire universe, including the parts that we can't see, is at least 250 times wider than that. And the universe could indeed be infinite in size. We've come a long way from simple speculation about the universe. Seemingly intractable questions are now getting answers, and that is your fascinating fact for the day.